Hey everyone, welcome to The Explainer. I'm really glad you carved out a few minutes of your day to join me. Today, we're going to take a calm, deliberate step back from our super cord-tethered lives to explore a piece of green technology that is honestly just as elegant as it is powerful.
So I want you to just pause for a second and ask yourself, what if your laptop literally never needed to be plugged into a wall outlet again? Seriously, imagine a world completely untethered from charging cables. No more frantically scanning the library or the coffee shop for a free socket, right? What if instead of being force-fed electricity from a grid, your everyday devices just breathed? Now, I know it sounds kind of like science fiction, but it's actually grounded in some beautifully simple chemistry that's already powering our world right now.
Okay, let's dive into this. Part 1, rethinking the battery. To really wrap our heads around how a device could just breathe to create power, we kind of have to rethink that standard lithium-ion battery sitting inside your phone right now. Think of a traditional battery like a water bottle. It holds a very limited amount of chemical reactants, and as you use your device, the bottle empties, and you literally have to stop what you're doing to find a wall outlet to recharge it. But a fuel cell, it operates on a completely different, honestly liberating principle. It's not a water bottle, it's a water fountain. As long as you supply it with fuel and oxygen from the air around us, it continuously generates electricity on the fly.
Which brings us to part 2, the liquid advantage.
So, if fuel cells are these magical energy fountains of the future, what exactly are we pumping through them? Well, hydrogen gets all the fame, sure, but dealing with highly pressurized explosive gas tanks isn't exactly something you want in your backpack, right? And that's where methanol brings a massive advantage. It's just a simple liquid at room temperature. That means it's incredibly easy to transport, but it still packs a super high energy density. Plus, it's way less flammable than gasoline, it poses very little risk to aquatic life, and when you use it in a fuel cell, it offers an exceptionally clean process with essentially zero harmful emissions. It's a pretty big game changer.
All right, let's zoom in a bit. Section 3, inside the machine.
So how does a machine actually extract pure electricity from a liquid without, setting it on fire? Inside the cell, you basically have two critical components, the anode and the cathode. You can just think of them as porous checkpoints or like gentle VIP gateways. They're the structural doors where our fuel, the methanol vapor, and our oxidant, which is just oxygen, actually enter the cell so they can meet and react.
Looking at the actual architecture, you can really see how these gateways do their thing. You've got the anode, which is this porous nickel plate impregnated with a platinum and palladium catalyst. This is the exact spot where our methanol enters. Then you have the cathode, which is coated with a silver catalyst, and that's where oxygen from the air is allowed to bubble in. Resting quietly right between them is our electrolyte, a fluid bath of potassium hydroxide, or KOH for short. When you add just a splash of pure methanol, that KOH basically acts as a bridge. It allows ions to cross over, but it actually forces the electrons to travel up and out through an external wire. And that external wire, that's what actually charges your device.
So the absolutely crucial point here is what happens when these elements finally meet inside those porous plates. And don't worry, it's less like some rigid math equation you have to memorize and much more like a graceful, microscopic chemical dance. Step 1, at the anode, our liquid methanol meets the hydroxide ions from that fluid bridge we talked about. They react and just cleanly release the stream of electrons. Step 2, at the cathode, the oxygen gas catches those traveling electrons as they return from powering your device, and they combine with water to form new hydroxide ions. And the grand finale of this whole dance, methanol and oxygen are peacefully converted into water vapor, a tiny bit of carbon dioxide, and a steady, continuous flow of pure electricity. There's no combustion, no roaring engines, just a quiet, continuous flow of power through catalytic oxidation.
Let's pan back out to the big picture. Section 4, powering our real world.
We've looked at the microscopic dance of protons and electrons, but how does this elegant chemistry scale up for us? Well, because it runs on such an easy-to-handle liquid, the applications are incredibly versatile. Think about a university research drone, for example. Instead of lugging around a heavy battery that dies in 20 minutes, a drone powered by a methanol fuel cell can monitor climate data for hours and hours just by sipping liquid fuel. Or imagine just snapping a tiny liquid cartridge into your laptop during a long off-grid camping trip instead of desperately hunting for a wall outlet. It's even being used to run experimental motor vehicles cleanly, totally avoiding the nightmare of storing pressurized hydrogen gas. It's just a remarkably smart, reliable solution for generating continuous power safely.
As we wrap up today's explainer, I want to leave you with a simple, peaceful kind of thought. When we think of generating massive amounts of power, we almost always picture giant, loud turbines or exploding combustion engines or the heavy industrial grid. But as the methanol-oxygen fuel cell shows us, the future of energy is all about smart, sustainable efficiency. progress doesn't always have to roar. Sometimes it just flows. So, what other areas of our daily lives do you think could be completely transformed by replacing a clunky battery with a quiet, liquid-breathing power fountain? I really hope this look into the quiet power of green chemistry has sparked your curiosity to learn even more about the incredible materials shaping our future. Thank you so much for learning with me today.